Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in engineering mathematics, angular motion. By the end of this tutorial, you will be able to calculate key variables in rotational motion, including frequency, angular velocity, angular displacement, and acceleration. This knowledge is fundamental for understanding gears, flywheels, and many other mechanical systems. We'll begin by analyzing the worked examples from the first page of your notes. Let's start with the first set of calculations. The problem provides us with the angular velocity omega, which is 37.037 radians per second, and the time t, which is 3 seconds. The goal is to calculate the angular displacement theta. The fundamental formula relating these three quantities is theta equals omega times t. This formula tells us that the total angle an object has rotated through is the product of its rate of rotation, omega, and the duration of that rotation, t. So we substitute our given values into the formula. Theta equals 37.037 times 3. Now we perform the multiplication. The result is 111 radians. Therefore, after 3 seconds, the object has completed an angular displacement of 111 radians. Next, let's look at the second example. Here we are given the same angular velocity. Omega equals 37.037 radians per second and a diameter d of 0.6 meters. Our task is to find the rotational frequency, n, in revolutions per second. The key formula here is pi times d times n equals omega. This equation links the frequency of rotation, n, to the angular velocity, omega, through the diameter, d. Let's substitute our known values. Pi times 0.6 times n equals 37.037. To solve for n, we need to isolate it on one side of the equation. We do this by dividing both sides by 0.6 pi. Calculating this gives us the frequency in revolutions per second. The frequency n is approximately 19.649 revolutions per second. The problem also asks for the frequency in revolutions per minute, or min. To convert from RAICE to min, we multiply by 60 since there are 60 seconds in a minute. So 19.649 times 60 gives us 1178.92 revolutions per minute. So we have successfully converted the angular velocity into rotational frequency in two different units. Now let's move on to the next set of worked examples, numbered 6. In this problem, a wheel accelerates. We are given the initial rotational frequency, n1, is 2 revolutions per second, and the final rotational frequency, n2, is 25 revolutions per second. This acceleration occurs over a time, t, of 4 seconds. The wheel has a diameter, d, of 0.6 meters. First, let's calculate the angular acceleration, alpha. Before we can use the formula for angular acceleration, we must convert the frequencies into angular velocities, omega. Angular acceleration is the change in angular velocity over time. The formula for angular acceleration is alpha equals omega 2 minus omega 1 divided by t. The problem actually provides a direct formula using frequency. Equals 2 pi times the quantity n2 minus n1, all divided by t. This formula implicitly performs the conversion to angular velocity. Let's use the provided formula. The symbol x is used here to represent the angular acceleration, alpha. Substituting the values, we get alpha equals 2 pi times 25 minus 2 divided by 4. This simplifies to 2 pi times 23 divided by 4, which is 11.5 pi radians per second squared. Calculating the numerical value, we get 36.141 radians per second squared. So, the angular acceleration of the wheel is 36.141 radians per second squared. Next, let's find the average angular velocity, omega bar, and the initial and final angular velocities, omega 1 and omega 2. We'll start by calculating the individual angular velocities. The formula is omega equals 2 pi times n. For the initial velocity, omega 1, we have 2 pi times n1, which is 2 pi times 2, giving us 4 pi, or approximately 12.571 radians per second. For the final velocity, omega 2, it's 2 pi times n2, which is 2 pi times 12, giving us 50 pi, or approximately 157.135 radians per second. Now let's calculate the average angular velocity, omega bar. This is simply the average of the initial and final angular velocities. The formula is omega bar equals omega 1 plus omega 2 divided by 2. Plugging in our calculated values, we get 12.571 plus 157.135 divided by 2. This equals 169.706 divided by 2, which is approximately 84,853 radians per second. Next, we will find the linear speed v of a point on the circumference of the wheel. The linear speed is the speed in a straight line, as opposed to the rotational speed. This is also called circumferential velocity. The formula that connects linear speed, v, to angular velocity, omega, and the radius r is va equals omega times r. The radius of the wheel is half of the diameter. The diameter d was 0.6 meters, so the radius r is 0.3 meters. The angular velocity we need to use is the final velocity after 4 seconds, which we calculated as 157.135 radians per second. Substituting these values, we get v equals 157.135 times 0.3, which equals 47.141 meters per second. So, a point on the edge of the wheel is moving in a straight line at a speed of over 47 meters per second. Following on from the previous calculation, we will now determine the linear acceleration a of a point on the circumference. Just as there is a relationship between linear speed and angular velocity, there is a similar relationship between linear acceleration and angular acceleration. The formula for linear acceleration is a equals alpha times r. The angular acceleration, alpha, was calculated in part A to be 36.141 radians per second squared. The radius, r, as we know, is 0.3 meters. Substituting these values, we have a equals 36.141 times 0.3. Performing the multiplication gives us a linear acceleration of 10.842 meters per second squared. This means that the point on the circumference is accelerating at 10.842 meters per second squared. Next, let's find the total angular displacement theta of the wheel after 4 seconds. We can use one of the standard kinematic equations adapted for rotational motion. The formula we'll use is theta equals the quantity omega 1 plus omega 2 divided by 2, all multiplied by time t. Notice that the term in the parentheses is simply the average angular velocity, omega bar, that we calculated in part B. In part B, we found that the average angular velocity was 84,853 radians per second. The time t is 4 seconds. So theta equals 84.853 times 4. This gives us 339.412 radians. The wheel has rotated through a total angle of 339.412 radians during the 4-second acceleration. We will now calculate the total linear distance s, covered by a point on the circumference during the 4-second acceleration. This linear distance is directly related to the angular displacement and the radius. The formula that connects these three quantities is s equals theta times r. In the previous part, part E, we found the angular displacement theta to be 339.412 radians. The radius, r, is 0.3 meters. Substituting these values, we get s equals 0.3 times 339.412. This calculation results in a linear distance of 101.824 meters. So, a point on the edge of the wheel has traveled a linear distance of 101.824 meters as the wheel spun for 4 seconds. Finally, for the worked example number 6, let's find the total number of revolutions made by the wheel. The problem asks for the number of revolutions. Let's call this x. The solution provided uses a direct calculation based on average frequency. A more standard approach is to use the angular displacement, theta. Remember from part YE that the total angular displacement was 339.412 radians. We know that one complete revolution corresponds to an angle of 2 pi radians. So to convert radians to revolutions, we divide the total angle in radians by 2 pi. This gives us 339.412 divided by 2 times pi, which is 54 revolutions. The solution in the notes uses a different but equivalent method. It first calculates the average frequency, NAV, as the average of the initial and final frequencies, which is 2 plus 25 divided by 2, or 13.5 revolutions per second. Then it multiplies this average frequency by the total time of 4 seconds to get the total number of revolutions. 13.5 times 4 equals 54 revolutions. Both methods yield the same correct answer. We have now completed the worked examples. Next, we will tackle the practice problems in Activity 2.2, one by one. The instructions specify to use pi equals 3.142 for our calculations. Let's begin with problem 1. The problem asks, a flywheel rotates at 18 revolutions per second. Its diameter is 0.4 meters. We need to calculate its angular velocity, circumferential velocity, angular displacement after 3 seconds, and the distance covered by a point on its circumference after 3 seconds. First, let's list our given values. We are given the frequency n equals 18 revolutions per second, and the diameter d equals 0.4 meters. Let's also calculate the radius r, which is half the diameter, so r equals 0.2 meters. We will use this radius in our subsequent calculations. Part A asks for the angular velocity, omega. We have the frequency n, so we can use the direct conversion formula. The formula is omega equals 2 pi times n. We'll substitute the given frequency, 18 revolutions per second, and the provided value for pi, 3.142. This gives us omega equals 2 times 3.142 times 18. Calculating this, we find the angular velocity to be 113.112 radians per second. The memo confirms this answer, which is 113.112 radians per second. Part B asks for the circumferential velocity, which is the same as the linear velocity, v. We can calculate this using the angular velocity we just found. The formula that relates linear velocity, angular velocity, and radius is v equals omega times r. From part A, we have omega equals 113.112 radians per second, and the radius r is 0.2 meters. Substituting these values, v equals 113.112 times 0.2. This gives us a circumferential velocity of 22.6224 meters per second. The memo shows 22.622 meters per second, which matches our answer when rounded to the same precision. Part C asks for the angular displacement theta after 3 seconds. We can calculate this using the angular velocity from Part A and the given time. The formula for angular displacement is theta equals omega times t. We have omega equals 113.112 radians per second and t equals 3 seconds. So theta equals 113.112 times 3. Calculating this gives us an angular displacement of 339.336 radians. The memo confirms our answer exactly. Finally, for problem 1, part D asks for the distance covered s by a point on the circumference after 3 seconds. This linear distance can be found using the angular displacement we just calculated. The formula connecting these is s equals r times theta. From part C, theta is 339.336 radians, and our radius r is 0.2 meters. Plugging in the values, s equals 0.2 times 339.3. The result is 67.8672 meters. The memo shows 67.867 meters, which again matches our answer when rounded to the same precision. We have now fully solved problem 1. Let's move on to problem 2 of Activity 2.2. The problem states that an axle rotates at 200 revolutions per minute. We need to calculate its rotational frequency in revolutions per second, its angular velocity, and its angular displacement after 5 seconds. First, let's write down the given information. The frequency is given as 200 revolutions per minute, or 200 rearmin. Part A asks for the rotational frequency in revolutions per second, n. We are given the frequency in revolutions per minute, so we need to perform a unit conversion. To convert from r-min to rs, we divide by 60. This is because there are 60 seconds in 1 minute. So nn equals 200 divided by 60. Dividing 200 by 60 gives a repeating decimal. The frequency is 3.3 revolutions per second. We'll carry this more precise number through our other calculations. The memo confirms the calculation by showing 200 divided by c. Part B asks for the angular velocity, omega. We can now use the frequency we just calculated in Part A. The formula connecting frequency and angular velocity is omega equals 2pn. We use n equals 3.333 revolutions per second and the value of pi, 3.142. So omega equals 2 times 3.142 times 33. Using a more precise value for 200 divided by 60 on a calculator gives a result closer to 20.944. The angular velocity is approximately 20.944 radians per second. The slight difference from the memo's 20.946 is due to the memo likely using pi equals 3.142 and a rounded value for the frequency, while I used a more precise value of 260. Part C asks for the angular displacement, theta, after 5 seconds. We can calculate this using the angular velocity from Part B and the given time. The formula is theta equals omega times t. We have omega equals 20.946 radians per second and t equals 5 seconds. So theta equals 20.946 times 5. This gives us an angular displacement of 104.73 radians. Again, using the more precise value for 260 gives us 104.733 radians, which is consistent with the memo. Problem 2 is now solved. We've reached problem 3 of activity 2.2. This problem is more complex as it involves uniform acceleration. It states, a wheel with a diameter of 0.5 meters takes 5 seconds to reach a circumferential velocity of 8 meters per second, accelerating uniformly from rest. We need to calculate the average angular velocity, angular acceleration, linear acceleration, angular displacement, and the distance traveled. Let's list all our given information, which is critical for problems like this. We have the diameter d equals 0.5 meters, so the radius r is 0.25 meters. The time t is 5 seconds. It accelerates uniformly from rest, which tells us the initial circumferential velocity, v1, is 0 meters per second, and the initial angular velocity, omega 1, is 0 radians per second. The final circumferential velocity, v2, is 8 meters per second. Let's start with part A, finding the average angular velocity, omega bar. To find the average angular velocity, we need both the initial and final angular velocities. We already know the initial angular velocity is 0, since it starts from rest. So omega 1 is u-rads. We need to find the final angular velocity, omega 2, using the final circumferential velocity, v2, and the radius. We use the formula v2 equals omega 2 times r. Substituting v2 equals 8 and r equals 0.25, we get 8 equals omega 2 times 0.25. To solve for omega 2, we divide 8 by 0.25. This gives us 32 radians per second. Now we can find the average angular velocity. The formula for average angular velocity is omega bar equals omega 1 plus omega 2 divided by 2. Substituting our values, we get omega bar equals 0 plus 32 divided by 2, which is 16 radians per second. The memo confirms that the average omega is 16 rad-ts. We have correctly calculated all the necessary angular velocities. Now for part B, we calculate the angular acceleration, alpha. Angular acceleration is defined as the change in angular velocity over the change in time. The formula is alpha equals omega 2 minus omega 1 divided by t. From part A, we found that the initial angular velocity, omega 1, is 0 rads, and the final angular velocity, omega 2, is 32 rads. The time t is given as 5 seconds. Plugging in the values, we get alpha equals 32 minus 0 divided by 5. This simplifies to 32 divided by 5, which gives us an angular acceleration of 6.4 radians per second squared. The memo confirms that alpha is 6.4 rads squared, so our calculation is correct. In part C, we need to find the linear acceleration, a, of a point on the circumference. This is related to the angular acceleration we just calculated. The formula that connects linear acceleration, angular acceleration, and radius is a equals alpha times r. We found alpha to be 6.4 rads squared, and the radius r is 0.25 me. Substituting these values, a equals 6.4 times 0 p r. Multiplying 6.4 by 0.25 is equivalent to dividing 6.4 by 4. The linear acceleration is 1.6 meters per second squared. The memo also gets 1.6 meters squared, so our answer is correct. Now for part D, let's calculate the angular displacement theta after 5 seconds. We can use the kinematic equation we used in our earlier worked examples. The formula is theta equals the average angular velocity times time, or omega 1 plus omega 2 divided by 2, all multiplied by t. We calculated the average angular velocity, omega bar, to be 16 radians per second in part A, and the time t is 5 seconds. So, theta equals 16 times 5. This gives us an angular displacement of 80 radians. The memo confirms the answer is 80 radians. This is a straightforward calculation once the average angular velocity is known. The final part of problem 3, part E, asks for the total distance s covered. This is the linear distance covered by a point on the circumference. We use the same relationship we've seen before, s equals r times theta. From part D, we know the angular displacement theta is 80 radians. The radius r is 0.25 meters. So s equals 0.25 times 80. Calculating this gives us a distance of 20 meters. The memo confirms the distance is 20 meters. This completes our solution to problem 3. Let's move on to problem 4 of activity 2.2. The problem states, the wheel of a bicycle has a diameter of 50 centimeters and rotates at 120 revolutions per minute. We need to calculate its angular velocity, the speed of the bicycle, and the distance traveled after 10 minutes. Let's list our given values, paying close attention to units. The frequency n is 120 revolutions per minute. The diameter d is 50 centimeters, which we must convert to meters, so it's 0.5 meters. This means the radius r is 0.25 meters. Part A asks for the angular velocity, omega, in radians per second. First, we need to convert the frequency from r min to r/rs. We divide the given 120 r min by 60 to get 2 revolutions per second. The memo uses a different formula, omega equals pi times d times n. Let's see if that works. Omega equals pi times 0.5 times 2, which gives us pi radians per second. Let's check this with our standard formula. Omega equals 2 pi times n, so omega equals 2 pi times 2, which is 4 pi radians per second. This does not match the memo's answer. The formula omega equals pi dn is not a standard physics equation. The standard formula is omega equals 2pn. Let's re-examine the derivation. We know that v equals omega r and v equals 2 pi rn. If we set them equal, omega r equals 2 pi rn. Dividing by r gives omega equals 2 pi n. Therefore, the correct angular velocity is 4 pi radians per second. This is approximately 12.568 radians per second using pi equals 3.142. We have found an error in the memo. The angular velocity should be 4 pi rad es, not pi rad as. Part B asks for the speed of the bicycle, which is the linear speed. The speed of the bicycle is equal to the linear speed of a point on the circumference of its wheels. We use the formula v equals omega times r. Based on our correction in part A, the correct angular velocity is omega equals 4 pi rad t. The radius r is 0.25 me. So v equals 4 pi times 0.25. This simplifies to v equals pms. Using pi equals 3.142, the speed of the bicycle is approximately 3.142 meters per second. Interestingly, the memo gives the answer 0.25 pms, which would have been correct if its angular velocity calculation was ph rads. Since we corrected the angular velocity, our corrected linear speed is pi ms. Part C asks for the distance s traveled after 10 minutes. Since we've calculated the speed of the bicycle in Part B, we can use the formula s equals v times t. The speed v is pi meters per second. The time t is 10 minutes, which we must convert to seconds. 10 times 60 is 600 seconds, so s equals pi times 600. Using pi equals 3.142, the distance s is 3.142 times 100, which equals 1885 meters. The memo gets 471.405 meters. This is because it used its incorrect speed of 0.25 pmls. 0.25 pi times 600 is indeed 150 pi, which is about 471.2 meters. So our corrected distance is 1885 meters. Let's move on to problem 5 of activity 2.2. The problem states, the wheel of a bicycle has a diameter of 60 centimeters and a linear speed of 40 kilometers per hour. We need to calculate its angular velocity, angular displacement after 3 seconds, and rotational frequency in revolutions per minute. Let's list our given values and convert them to standard SI units. The diameter d is 60 centimeters, which is 0.6 meters, so the radius r is 0.3 meters. The linear speed v is 40 kilometers per hour. To convert to meters per second, we multiply by 1,000 meters per kilometer and divide by 3,600 seconds per hour. This gives us v equals 11.111 meters per second.